Welcome to the talk about domain-independent interprocedural program analysis using block abstraction memoization. My name is Karl-Heinz Friedberger and this is joint work with my supervisor Dirk Bayer. We are from the LMU Munich in Germany. Since several years, software verification has been successfully applied to improve the quality and reliability of computer programs. On the slide you can see how software verification works in general. Starting with a C program and a specification like not reaching the function error, the verification tool provides a proof whether the specification is satisfied and returns true, or it returns false when a bug is found or a counterexample trace can be confirmed. In general, the verification tool creates an over-approximation of the reachable program states and computes program invariants. The idea is that no error state is part of the reachable states or part of the over-approximation. Several verification tools simply enumerate the reachable state space and do not take care of the structure of the program. This causes problems, and we will show with the following example which problems there are. This example program computes the sum of two non-deterministically initialized variables a and b. If the sum is correct, the program is valid. If the sum is incorrect, an error function is called and the specification is violated. The procedure sum is recursive, which means that sum itself calls sum internally. The control flow automaton of this program shows the recursion as a cyclic dependency in the procedure sum. You see the green arrow on the right side as a recursive call of procedure sum. This program cannot be verified by a bounded model checker that unwinds the recursion, because the number of unrollings is unknown. The verification approach needs to apply a summary of the procedure instead of the recursive call to verify this program. Such a summary could specify that the return value of the procedure sum is equal to the sum of the parameters. A program analysis that applies procedure summaries is called interprocedural, because procedures can be analyzed separately and verification results are merged together afterwards. In the next few minutes we will define such an interprocedural program analysis based on well-known components like the CPA concept. The concept of CPA, or configurable program analysis, is a domain-independent approach for abstract state space exploration. It defines a fixed point algorithm for the state space exploration and operators for specific domains. Example operators are the transfer relation that computes successors, a merge, and a stop operator. The merge operator combines abstract states and the stop operator checks whether one state is covered by another state. By defining operators for specific domains, the algorithm itself is independent of the used domain. And we can use several domains like explicit values, intervals, or predicate domain. We can even combine several domains to harvest their strengths. The concept itself is not yet sufficient for an interprocedural program analysis, because it's not modular. There is only one analysis for the whole program. There is no chance of applying procedure summaries. However, there exists an extension of this concept, and this is block abstraction memoization, which is a divide and conquer approach that splits large verification tasks into smaller problems. It divides a program into procedure blocks or loop blocks and then solves the analysis for each of the blocks separately. It uses a CPA algorithm for the domain-specific part, so it is itself domain-independent. And intermediate results like procedure summaries can be cached and reused. This approach inherits the domain independence from the CPA concept, and allows us to simply reuse intermediate analysis results. This already sounds like the verification approach that we wanted to have. However, this is still an intra-procedural analysis approach. The context of each block is relevant for the block's abstraction. Due to its domain-independent approach, we cannot yet handle colliding variable names from different procedure scopes as they happen, for example, for recursive programs. And at this point, we contribute our inter-procedural block abstraction memorization approach that is based on the intra-procedural one. We define 3 operators for specific domains: the reduce operator, expand operator, and rebuild operator. The reduce operator computes an abstraction when entering a block. The expand operation is the complementary operation and computes a concretization at block exit. And the rebuild operator is the one that is important for recursive procedures. It restores context information from the calling procedure when leaving a block. An additional fixed point algorithm computes a sound opera approximation of the recursive procedure when unrolling the procedure calls. In each iteration of the fixed point algorithm, we increment the number of unrollings of the recursion and compute an over-approximation of more paths through the recursive procedure. The algorithm terminates if coverage was reached for all analyzed recursive procedure calls. For a detailed explanation of the operators and the fixed point algorithm, please take a look at the paper. In the following, we will present an example how to apply this algorithm to the previously given example program. We apply a predicate-based domain combined with our new approach for interprocedural program analysis to verify this program as correct. We assume that the predicate-based domain already has the necessary predicates, and we just show the steps that are required for our own algorithm. For this program, our fixed point algorithm requires 2 iterations. In the first iteration, the non-recursive part of the procedure sum is analyzed and the procedure summary is computed. This procedure summary is then applied in the second iteration of the fixed point algorithm to summarize the recursion, and the fixed point algorithm terminates afterwards because the procedure summary is sufficient. The figure on the right shows the abstract reachability graph for the first iteration of the fixed point algorithm. The labeling of each abstract state consists of the program location, that's the circled number in the first line, the call stack, that's the second line, and the abstraction formula of the predicate analysis in the third line. Each state is annotated with an index to show the order of computation. Procedure blocks are highlighted with gray borders. The red arrows and blue dotted arrows show the operations that our interprocedural analysis applies. The underlying CPA algorithm applies the predicate analysis and computes successors for each abstract state. Starting from the state in the upper left, labeled with E1, that has a call stack of the main function and an abstraction true, we compute successors until we reach the function call at location 11, where a new call stack is computed, the call stack main and sum, and a new abstraction is computed that is also true. At this point, BAM applies the reduce operation and reduces the call stack to only sum, without the main function that is out of context of the procedure block that was entered at this location. After entering the procedure block of the function sum, an independent sub-analysis using the CPA algorithm is applied. It computes successors, in this case on the left side, the non-recursive path through the program using the abstract states E6 and E8 is computed. On the right side, E7 and E9 are computed. On the state E9, we reach the recursive call of the procedure sum and enter the function block bsum again. At this point, we apply the reduce operation of bum and reduce the abstract state. The call stack sum and sum is reduced to only one sum, which means the calling context of the function call is removed. The abstraction true remains true because it's already abstract anyway. This is the first iteration of the fixed point algorithm, so no block abstraction was already computed and the cache is empty, which means for this recursive call we cannot yet apply any existing procedure summary and we get a cache miss. That means in this case there is no successor for the call of this recursive function. The analysis continues with the non-recursive branch of the program and reaches state E8, where an abstraction is computed, return value equals the sum of the parameter values MP and NP. The state E8 is then expanded and rebuilt into the calling context of this procedure block. The call stack in the second line is expanded from only sum to main and sum, which corresponds to the full call stack again. The abstraction formula return value equals sum of the parameter values is rebuilt into a form that only consists of variables that are available in the calling context. Afterwards, the CPA algorithm continues with the successor computation until it reaches the program exit. In this iteration, we did not yet reach any property violation, but we did also not yet prove safety of the program, because we did not yet apply a procedure summary within the procedure block. Thus, we need a second iteration of the fixed point algorithm. The second iteration of the fixed point algorithm starts at the program entry again and computes in the beginning the same states as in the previous iteration. When reaching the abstract state E29, we call the recursive procedure, and now we have a procedure summary in the cache that can be applied. In the image, this is the nested gray block on the right side of the right figure. When applying this recursive procedure summary, the exit state E8 is also expanded and rebuilt for the calling context to E32. The call stack is expanded to a full call stack of the calling context, which means that the call stack sum is expanded to sum and sum. It's a recursive function, thus it's twice. The abstraction formula return value equals the parameter values MP and NP is replaced by an abstraction formula that talks about the local variables n and m. Please note that the return variable red is available at this location because it's the return edge in the control flow automaton. In the next steps from E32 to E33 and E34, the return variable changes. That's a different return variable at the location 16. The CPA algorithm will notice that there is a coverage relation, here marked as coverage 2, between the state E28 and E34. This coverage relation avoids that a new state is reached at the exit of the block bsum at this point. When leaving this block, we only have to apply the expand and rebuild operation for the state E28 and not for the state E34. And that's the termination criterion for the fixed point algorithm. There is no new state within the recursive block. The CPA algorithm afterwards continues with E35 until E37 and does not reach the error location or the property violation in the program. Thus, the program is safe. We have seen a sound analysis of a recursive program that was done by the interprocedural approach of block abstraction memorization. Our work does not only contribute a formalization of this interprocedural program analysis technique, but also defines the necessary operators for 3 different abstract domains, namely the value domain, the predicate domain, and the interval domain, which differ in their representation of abstract information in the state. Based on the CPA concept, we also allow a combination of domains, which can be seen in the following, where we combine a value and predicate domain. Our approach does not need to be applied alone. It can be combined with different approaches like counterexample guided abstraction refinement or witness validation. An implementation of our approach is available in the open source software verification framework CPA Checker that is developed at the LMU Munich. In the following, we compare our implementation in this framework with other approaches implemented in the same framework and also other tools that are available for the verification of recursive programs. To show the effectiveness and efficiency of our approach, we have chosen over 1000 non-recursive tasks from the SV benchmark suite and over 100 recursive tasks from the SEM suite. Our evaluation consists of 2 different parts. The first part is an evaluation within CPA Checker, where we compare 3 different analyses and 4 different domains, or 3 domains and 1 combination of domains. The second part of the evaluation is a comparison on recursive tasks, where we compare several participants of the latest software verification competition and show that our approach is competitive. The benchmarking was performed on our cluster using an Intel Xeon CPU with the limitations of 15 GB of memory and 15 minutes of CPU time. Let's start with the comparison of our new approach within CPA Checker against other analysis, also within CPA Checker, on different domains for non-recursive tasks. Here you can see the number of correct results from the benchmarks for 3 different domains: value domain, predicate domain, and interval domain, and a combination of domains, value and predicate. You can see that the green plot the proofs and bugs found by BAM interprocedural, which corresponds to our approach, is in nearly all cases as good as the existing analysis. For the predicate domain, we got less results due to an unmatching interpolant that caused an expensive unrolling of loops, but this does not correspond to procedure summaries. This plot shows the results for non-recursive tasks. On the next slide, we show the same analysis, the same evaluation, but for recursive tasks. Across all domains, there is no relevant number of results for any analysis that is not based on our BAM interprocedural approach. This shows that there is a clear benefit of our approach within CPA Checker, within one software verification framework. What about other tools? How do we compare against other tools, for example those that participated in SVComp 2020? This table shows those verifiers that provided a relevant number of correct results in the latest SVComp. There are major tools like CBMC or ESBMC that apply bounded model checking without any function summaries. There are tools like Ultimate Automizer in the second last line that provide function summaries. And there is CPA Checker that applied a combination of value and predicate analysis based on our interprocedural approach to verify recursive procedures. As you can see, the number of found bugs and found proofs is similar, and the CPU time is not much higher than other major tools. In summary, our approach provides a modular, domain-independent interprocedural analysis with components that are based on an intra-procedural analysis in the framework of CPA Checker and can be combined with more components of the same framework. We provide support for recursive tasks and provide the necessary operators for several domains. The evaluation has shown that there is only small overhead against other analysis in the same framework, so BAM interprocedural is competitive with BAM intraprocedural or can replace it, in most cases, for several domains. And against other verifiers, in the SVComp 2020 we showed that there is a competitive performance on a larger set of benchmarks. For more information, we refer to our paper Domain-Independent Interprocedural Program Analysis using Block Abstraction Memoization from FSE 2020. You can also download our reproduction package. The URL is given here. It was labeled with artifact available and functional. Or you take a look at our implementation at the open source software verification framework CPA Checker. Thanks for listening.